So we're going to have a bit of a look at how it might sound when they are performing.
DJ Orbit on the left, and DJ Odelin on the right.
So obviously these sounds that they are scratching on, they come from the computer. They recorded them themselves because they are mentioning their own names, and probably they don't have their names on real vinyl. So.
Beats and rhymes. I'm feeling trapped. Can't stop the bro. It's impossible. Can't stop.
And you see, what he did here was that he pressed this panel, and that changed the sound. So it controls the computer to change the actual sample that is replayed. So you can switch in between different songs directly by pressing these pads or different sounds. And you can make music. And there you also saw that he was re-triggering the same sample position several times to have it taking this saxophone tune and making essentially new music from old music. So that is what DJing is about, and these guys, they are really, really skilled. It takes years and years of training to get to the point where they are, that they can actually not only scratch, but make it sound good. At least to me, it sounds great. So how does this work? What is the technology behind this magic that you can get the computer to act as a vinyl player? So I'm going to take you through that, and that is a Rust journey, and it starts with MATLAB or Octave in my case. So I was trying to model the control signals and see how we can recreate the position, because the important thing here for the computer to know is where on the record are you at the moment. And it will use this information to replay or resynthesize the sound output. And now I'm a bit handicapped because I have just one hand. The other is holding the microphone. So how does this work? Let's see if we have a network here. Not so much. Yeah, but it's connecting to Tune, and I think it should work. But in the meantime, maybe we can see this. This is the repository that is under Per Lindgren, Face Track, and it's open, so you can go to here and have a look at it. And yeah, I think now it has a README, but it's not shown here because we don't have the latest version. Right, so we can stop there and maybe take a look here. So finding out position is a common problem. I mean, we are doing it now when I'm scrolling here with the scroll wheel. It uses a quadrature detector. So it's actually tracking the position of the scroll wheel by a phased signal. So there are two signals. In this case, they are like square waves with a phase offset. And then there are some either electronics or software that actually unfolds this into a position and direction. So you can both get the direction and the speed, and out of that, you will be able to track the position. And this final record uses a two phase-shifted sinus signals encoded as left and right, because that is what you have on a stereo recording. So it's a stereo waveform with two sinus signals. It has been hugely successful. these DVS systems are widely used by both live DJs and music production. And it's very robust and accurate tracking based on this. And flexibility, as we see, they are scratching and DJing on sounds that they made their own. That's not available on vinyl. So the solution is a well-known tracking problem. So it's not a new thing that I invented or they invented, the ones behind these systems, but it has a well-established theoretical foundation. And I will show that in a bit. So we use Octave, which is a MATLAB-like tool for rapid prototyping and visualization of waveforms. And then later we'll show a one-to-one manual transition or translation of the MATLAB or Octave code into Rust. And here there are some interesting functions that are not part of standard Rust. So we are using libm, which is a great library for mathematics. And we are using the RAND library to get random numbers because we want to test how resilient to noise this tracking is. And then we are using the plotters crate. Anyone has seen that? Maybe you're already using it. It's great. It's not so easy to use, but the results are good. And then for quality and assessment validation, we are using CSV format, so we let Octave output the sort of golden model results, and we read them into Rust, and we are computing the error. And in this case, we are using, I think I can show that, this mean squared error function looking like this. It's also a well-known measure for assessing quality. And we can see that we get an excellent correlation in between the MATLAB code or the Octave code and the Rust implementation. And it might even be that the Rust code is actually more correct to the problem than Octave, because this libm does a lot of smart things when it comes to calculations of small angles. Well, x is near 0. You can read more on the Git if you're interested in more details. So without further ado, we're going to look at this, where we have some Octave code, and we'll start with this phase M. So what we're doing here is that we're actually over a period of 48,000 samples, which is a common sample rate. We are producing a sinus and a cosinus signal. So these are then phase shifted according to each other at the frequency of 2 hertz. And the sample time is 1 second. And what we are doing here is to compute the arctangents 2 function. The tangents function is the relation in between height and width. So you can use that in trigonometry. And arc of that is just the inverse function. So you can get a phase value out of the 2 left and right signals. Essentially, it says how far in, if you have a sinus signal like this, how far in are you on that? And by having 2 of them, you can discriminate in a much better way. So that's why we have left and right. That also allows us to track the direction, as we'll see later. And then there is a problem here. That is, when we are reaching the end of the first period, a new period starts. But the sample values will be exactly the same for the first and second and third and fourth period. So we have to check when we are entering a new period, and that we're doing here, and we call that the wrap value. So when that happens, that means that we are increasing the wrap value here, and that is used to create an unwrapped signal. And now we can run this. So we can start the terminal, and we can have MATLAB or Octave. So we start Octave like that, and we can CD into octave, and we can source this MATLAB script, which is called phase.m. So what we are seeing here are three graphs. The first graph is the sinus and cosinus, and we can see here that it's two periods. So this is the first period up till here, and then the second period up till here. And then we can see the A tan 2, that is this, the value, we can see that it's increasing up to half of the period. Then we have the next for a full period. It's increasing again for half a period. And then we have the unwrapped values over here. So this one is tracking the total position. So it takes the wrapping into account. So this is it's nothing spectacular with this. This is a well-known technique for finding a position. You can use it inversely for tracking time if you know the frequency here is stable. So then you can also see how long inside a function you are in terms of time. So time and position might be interchanged. Right. So you get the basic idea how this works, that on the vinyl we have these two sinus and cosinus signals. We read them through a sound card. We just sample the signals, and we detect the phase of it with a tan 2 function, and we unwrap into an absolute position. Well, absolute in relation that we know the start position, but in general it will be a relative position. But the idea is the same. Okay, so how does that work if we change the frequency over time? So we have a phase inc here. Let me see. It's awkward with the microphone. Now what is this? Phase. Here we go. Inc.m. And then we see unwrapped signal looking a bit like this. So what's happening here is this is the arctan, and we see that the density of these are increasing because we're increasing the frequency. We can also look at this graph showing that in the beginning we have a low frequency that we start out from, and then in the end it will be chaos of sinus signals here. So the density is increased here by the rate and frequency is increasing. And we can also see that we have a growth here in the position. So that looks good. It's expected, right? This is exactly what we want. So what about direction? Can we say something about that? Well, this one. This one is interesting. We start out with a signal that looks like this. Here we go. So we start by forward, increased sample positions, and here the frequency goes to 0, and here we will have a negative frequency. So we are sort of pushing in relation to the DJ. He would push the record forward and then drag it backwards. And this is the position where it ends or does not move at all, so it's the turning point. So how would the phase angle look like? It would look like this. Here we are going forward, and here we are turning, and here we are going backward. And we can also see that the position is increasing here while it's decreasing over here. Here it's first increasing, then 0, and then starts to decrease. And the unwrapped counterpart looks like this. So this is the actual tracking of the signal after that we have done the unwrapping of it. But it's not so obvious to see directly from this but we can also see here that the red comes before the blue, and here we have the blue coming before the red. I don't think the colors are really consistent within the graphs. Probably possible to give them some deterministic colors, but I'm no Octave expert, so I just got this to work. Not anything more. Phase noise, so what about that? It's important for any tracking that it's resilient to noise. So let's have a look at this. How does a noisy signal look like? Now, this is really, really noisy. This is really, really noisy. Here we have about 25% noise in comparison to the actual signal. We can still see that since the noise is just overlaid over the sine and cosine, we can still see that they have some form to them, but we have a lot of uncertainty. So how do the tracking deal with this? So we can look at, let's see, maybe, yeah, we can go directly to the solution. Here we see that we can see that the A10-2 has a lot of uncertainty to it, but we can still unfold or unwrap the correct signal. So on the average, if we make a bit of a low-pass filtering here, it would look perfect again. So that means that it's really robust. 25% noise, that would be approximately 2 bits. If you are sampling with 2 bits, then you will get that bad signal to noise ratio. But we can push it. This is the phase noise. So let's have a look at this, how it looks like. So here is just to offset, the rand function gives random values in between 0 and 1. So we want to have it centered around 0. And here is the weight. So the signal would go from -1 to 1. That's why 0.5 means that it's 1/4. But let's double the noise. Oops, not there. Let's double the noise to 1 and see how that performs. And now we are really, really noisy, as we will see. So let's go back to here. Maybe it did not work. Let's see. If I do it like this, I don't see the end of my, because this one has, I want to close this. And I want to close that one. And I want to close that one as well. I don't know why it behaves like this. We can take this down. And there are still some, yeah, now we have the right one. Here we see the one that has a lot more noise. So let's see how the phase unwrap. No, this is the wrong one. And let's see here, this is also the wrong one. So let's rerun this again and hope for the best. Phase noise. Yeah, so now we see that we have a lot more noise here, but we are still tracking perfectly the transitions. The unwrapping is working. So let's go really, really mad and put 1.5 here. That means that we have 75% noise in the signal. And we can see that the noise here increased by that, but the unwrapping succeeds. And here we have the actual signals, and they look like shit. Obviously, it's very, very noisy. So what we can conclude from this is that the tracking here is very, very stable, even under extreme noisy conditions. And think about the DJ, he's pushing the platter, the vinyl, back and forth at a very high rate. And you have this mechanical device that you just hope to work. So it's this cartridge or pickup. It might bounce around a bit. So it's really good that you have a stable tracking algorithm. So we can push it a bit more, and then you will see how it breaks down. If we put exactly the value 2 here, that will mean that we have the same amplitude in the noise signal that we have in the actual signal. And as we see here, there is no order in anything, it's just random. Well, maybe you can sort of feel that it's an increasing signal, but yeah, well, it might also be dependent on how the rand function works. It's not really random numbers, it's a sequence that a computer computes. So it's deterministic. And well, that might be an artifact of that we are seeing here. But essentially, this will never happen in reality, so we don't need to worry too much about that. So we can put it back into the like more reasonable 0.5 and 0.5 over here. The algorithm here is exactly the same as I showed the first time. The only thing is that we also have to check for the wrapping in an opposite direction if we are going to be able to track the record turning and going backwards. But besides that, all is equal. And here it's just plotting code. So the MATLAB part of it is really, really simple. Any questions so far? This is certainly useful to other things than DJing, but mostly to DJing, I would say. So examples here in Rust. What we have here, let me close that, is a Rust program. And we could put this face.m in parallel, just as a comparison. And now I'm not much of an Octave or MATLAB programmer, which means that I write MATLAB code like I would have written Rust code. So we can see here that this is setting up a range. Here we are doing the same thing with a range in Rust. We are computing the sine and cosine into a vector directly in this case. Here we are doing it for each element, element-wise. But besides that, we can see that the code here, we are checking the tan2, blah, blah, blah. Everything is essentially the same. So we can see that this for loop is exactly the same as this for loop. And the plot here corresponds to the plot here. And then we also do a quality assessment. So we can try running this. If I now, not sure why, it says that it's terminate task, okay. Well, it did terminate in the end. So what happened here is that it computes the accumulated error for these 48,000 samples, and it's really small, and this is the MSE, so it is the mean square error. And it's even smaller because each error is so small. I don't know if these are the right measures for this purpose, but at least it's some measure, meaning that we see that these correspond really well. And it's the unwrapped signal that we are comparing. So I put some code in a library here, which does some like file loading to read a CSV file. Here, what we're doing here is the quality assessment, and it's just iterating over these two arrays and accumulate the errors and the accumulated error and the mean square error. So it's very simple Rust code in order to compare these two, and then it just prints accumulated error. The rest of this library is horrible. It is the plotting code for the Rust part. I don't know exactly what happened here, but we can have a look. We have SVG files generated. and we can preview the SVG file, and it looks like this. We can relate that to one of these, the initial one that I showed from MATLAB. The wrapped signal we can look at as well. That does not work anymore. Sorry, let's see again. So we have the wrapped signal. Preview that. Why is it? Yeah, it is working. So this is the wrapped signal, and the unwrapped signal. Preview of that looks like this. So obviously they look very similar to the graph that we saw plotted by Octave earlier. And also the error assessment that we did showed that these were the same. We can do exactly the same for the phase decrease and the noise part. Maybe the noise part is the more fun thing to look at. So we can run that and press run here. Okay, it's already done, I guess. So it's really fast since we are just processing 48,000 samples. And now we have SVG files for this. So this is the noisy signal. What we have more is the wrapped signal over here. No, we don't want to look at the SVG file, but we want to print it. So this is the that part, and the unwrapped is this. So we can see that also for the noisy part, it worked out. It's harder to do error estimation if we have noise involved, because the noise will probably look different from MATLAB and from Rust. What one can do is to generate a file with the noise, so we have a replicable noise, and then it would have been possible to compare. I didn't do that because I think this is simple enough to trust that the measurements that we did earlier on also hold in the case of the noise. So now we know how, or at least have a good idea, how we should be able to replicate or at least track the control signal. So what can we do with that? Well, we can do what they used to do. I mean, have the computer just replaying a sound according to the positions that DJ gives through the vinyl. But we can do more. And this is, to my knowledge, no one has yet done. And that is an editor. So this is Cut Creator. I think it's the first editor for DJ scratches. So what we can do with this, it's written in Egui, is to open it up like this. And here we have a plot of the record position. Maybe, can we get this to work somehow? Well, nothing works. This is...
Well, it worked half an hour ago.
Yeah, but obviously it does not work now.
Yeah, sounds like it could be better.
Or just, we try to...
Yeah,
Yeah, that was the only thing needed. Okay. So what do we have here? Well, we have the sample to the right. We can enlarge that if we want. So this is just a sample. It sounds like something like that. And here we have the scratch positions. So that would correspond to this unwrapped signal. And here I'm using splines interpolation in order to be able to edit the positions. So here that would mean that the sound will go forward, backwards, forward, backwards, and then finally forward. So we can press this sample button, and then with a bit of luck we can find it, and we can read. So we had a wee, wah, wow. And I started this without any knowledge of Egui. Actually, I think it was one of you guys that showed his iPhone that he was running Egui on it, and he had a snake game running or something like that. Yes. It was maybe not a game, but at least it showed that it was possible. So I mean, it is possible. And Egui is quite nice, and a direct mode renderer for GUI applications. So what you write in your code is going to be displayed as is. So it's nothing. You don't set up a complex data structure in order to capture the layout, what you want. But it's very, very direct, and it's easy to do things like this. So we can actually have it working. If I know how my GUI works, Control O for oh, okay. The thing is that it opened this here. So we can have another one here, no, like that. So we can edit multiple scratches at the same time, and we can, these we can shift click and like this, and we can remove, or we can also undo with a bit of luck. Maybe that does not work. Well, maybe it does not work with two open windows. This would, in the future, represent the fader position. I did not yet implement that. But there is a lot more that can be done. We can load different types of samples here. These samples can be edited with a bit of luck. Yeah, so we can, now this does not completely work. Yeah, in any case, you should be able to scroll. Yeah, you can grab and offset the position, and you can zoom in and zoom out, which affects where these cuts are sort of related to the actual audio sample. So it gives you a lot of flexibility when it comes to the reproduced sound. And the idea is that it should be really, really fast for a DJ to use. So everything is shortcutted. So you can enable and disable different tracks just by a direct selection, a bit like what they were doing when they pushed these buttons. So the idea is that it should be a really tactile tool for working with scratches like this. And then, well, I don't know if there is so much more to see. We can take and grab, and we can also push around samples. You can see that these knots here cannot go over the edge. Instead, you would be able to do something like, I'm not sure if this works, but yeah, you can grab many of these and offset them in time. And these time slots here would be a representative of the beats in the music, so you can align them to certain beats or positions in the song where you want to sort of have this sound overlaid. Any questions? This is completely open source, and anyone can contribute to the world of DJ scratches. Yes?
Hey, quick note about the question policy. We have a microphone here, so I'll bring it over to whoever tried to get my attention, so I bring the microphone over.
Yeah, thank you. Amazing presentation. I just want to ask about the basics from the beginning. So did I understand you had a picture where you had these two sine waves with a phase difference, and the frequency was increasing to the right?
Yes.
And is that what you put on the vinyl? So you have a vinyl with left and right channels?
On the vinyl, you have just a fixed frequency. So like 1 kilohertz is good, because then it allows you to push the record 10 times faster than nominal speed and still be within the limits of what a magnetic cartridge can pick up. So
all right.
So what this the graph that looked like that maybe that would symbolize that you're actually increasing the speed of the record. So it starts from very low speed and then you're pushing the record very fast forward.
Yeah, that makes sense. I was thinking about if you lay the needle down somewhere on the vinyl, then it doesn't know the position at all.
Position. It does not have any information on where it is initially. That's why they have these buttons to start a sample. So they use this to trigger a specific starting point. But there are also more advanced ways of doing that where you overlay a positioning signal. And that is also a possibility to do. And then the decoding of that would be a bit more complex than this.
Cool. Very, very interesting and informative.
So records are not linear in the sense that the frequency is not represented linear. There's some curve to, because otherwise a very low frequency would be too long. So there's some sort of curve they apply to the signal before when it's recorded, and then there's the inverse curve done when the signal is played back normally.
Exactly.
So are you actually capturing the raw signal, or are you running it through this correction curve?
What you're talking about is this RIIA.
Yes, I didn't want to say that because no one knows that, but that's what it's called, yes. I wanted to say what it does.
Yeah, well, since we are just concerned with the phase angle, the amplitude of the signal, we don't need it.
Right, so you don't, because
we don't need it for tracking, which means that, it's actually a good thing that this curve exists, because it plays in our hands actually regarding the robustness of this. But we can take that offline and I will discuss why it's like that. Okay. But it's a good thing that we have this compensation or sort of filtering of the signal.
Yeah, that is like a...
Thanks. How big is the impact of using the Liben library for the 8 and 2 function?
The implementation?
I mean...
or do you mean the execution time for it?
No, I mean mostly the error. Like you're now using the Liben functions 8 and 2 instead of just using the standard libraries 8 and 2 functions. Is the 8 and 2 function from the Liben function much more accurate, or...?
From my understanding, it tracks the problem when you have, it says already here, maybe it was somewhere here, 8.10.2, this is from there, this is taken from their website. And it says it produces the correct results even for angles near pi divided by 2 or minus pi divided by 2. So my understanding of this is that the A tan 2 is problematic because you run into rounding errors, and actually what it's called is underflows. And if you don't handle these underflows, or if you handle them incorrectly, you might be way off. And their implementation, to my understanding, is never way off. So it takes this sort of underflow conditions into account when producing the result.
Did you first try it with the standard libraries?
No,
8 and 2?
I'm not even sure that this function exists in the standard library.
Oh, I think it does, but I might be wrong too.
It might. But I found this with the first Google search, so
yeah, thanks.
that's the plain reason why I used it. Yes.
Yeah, so I noticed you use a lot of 64-bit floats for this, and I guess it doesn't matter on a fast computer like a laptop, but if this was implemented on like a microcontroller in like hardware, have you tried using like smaller data types with less precision?
No, I haven't for this experiment. I haven't tried it.
Okay.
Actually, the playback that I showed, that used just 32-bit floats.
Okay.
So for the actual implementation, I will probably settle for 32-bit. If it seems that we can get sufficiently good tracking because it's more computationally effective.
Yeah. A lot of microcontrollers don't have floating point units, so they use fixed point math.
Yeah,
usually
that's
16
also
bits.
possible. And I haven't looked at the implementation details that closely yet.
Okay.
And the idea is to this code will in any case probably run on a laptop or similar. So it's not an embedded for now at least.
Okay.
So what is the takeaway here? Well, we can make a lot of funny noises with the help of a computer, a turntable, and a cartridge picking up this control signal. And I can show you this. No, I could not because I closed it. But these records that have this time code on it, they are quite widely available, and they cost like I would say €15 or something. So it's not a super expensive thing to get going with. And you can just use your normal audio interface on the computer if you're satisfied with just one turntable or a usual sound card with multiple inputs. There is nothing. You can actually connect to that directly if you want. If you have a converter for the vinyl, you need to have a preamp for your vinyl player. This is not the only way to do it. There is also a wireless solution that is called Phase for some reason, a French company that developed this, and it uses an accelerometer instead of the control vinyl. So you put an accelerometer on the platter to track its position. But essentially what it does is to replicate these sinus and cosinus signals out of it, so it acts as a turntable in the end. So they made just the sensor part a bit different, but the actual tracking is done in a similar way on the computer. Yes, you have one more? They all also do that, but their protocol is not open. Yeah, if you want to have a go at it, please. Yeah, I have. Yeah. Yeah.
It's on.
So you had the interesting noise analysis at the beginning. I had another concern that one of the most scary bit about signal processing to me is the concept of aliasing. So what if you spin the record too fast, and then you basically see those signal transitions all the time? Now, can you spin it like exactly the speed where you would think that where the software would think that it's spinning the other direction or something like that? Or
I don't think
maybe it's not a problem if you're spinning it so fast it becomes.
Yeah, I think
too bad anyway.
As I said, the problem with having it stored on vinyl, originally the sort of carrier wave here, is that when we speed up the record up to 10 times, then we have a 10 kilohertz, not a 1 kilohertz signal. If we do it 20 times, then it's questionable whether the pickup, the actual cartridge, will be able to reproduce this as a sine wave. And also the sound card is so limited. In this case, it was 48 kilohertz as a sample rate. You can go up to 96 or something. But I think the physical limitations of the vinyl would hit us before the sound card or the sample rate is a problem here.
Makes sense. Thanks.
Yeah. So that's the idea, at least. And in practice, this is very much used, and it is replacing vinyl because vinyl is hard to come by. So a lot of DJs are using these systems, both the phase one and the one with control vinyl. So please approach me.
Yeah, there's
One more question.
Yeah.
So you showed the very neat editor where you were able to like simulate these scratches and then reproduce the audio. Have you experimented with doing the reverse? So basically recording the scratching signal that someone is making on a physical vinyl with the signal, and then like recreating those, like constructing those control points in your GUI that you could then edit later and like improve on the scratching performance later on.
Yeah, well, actually, that is exactly the next step. But I want this to work within a DAW, in a digital audio workstation. And there you are presented with sample buffers from the DAW, and you are returning sample buffers. And you can have samples incoming. So this signal that we were picking up from the vinyl record could be presented to the plugin, and the plugin could do the analysis online. And then we can have some sort of I would say splines alignment function that tries to minimize the error of the splinification, so to speak. I haven't done that, but it's certainly on the to-do list. And since it's an open source project, if you find this fun and interesting, please approach me and we can discuss how this could be done. Because I'm no expert at this yet, so.
Amazing, thank you.
Okay, I think we are going to cut off the questions at this point. So the update on the timetable, or not much of an update, but the fact is that the pizza will be arriving in something like 10 minutes. And after that, I think we'll be, so let's have a break until that so we can handle that with minimal hassle. I'm going to need like 2 or 3 volunteers because it's actually quite a logistical issue to get 17 large pizzas upstairs from down there. So I'll be open for applications in several minutes. But other than that, after the break, we will be continuing with the more traditional theme of Tampere, that is embedded systems. So I think we have 2 talks that go closer to that kind of theme. So there's actually quite a large community of embedded Rust going on in Tampere at the moment, which I am very happy about. And I just, somebody came to me during the presentation to say that there's possibly some job openings also that they would like to talk about. So would you like to introduce that now since we have the 10 minutes, or do you want to take it later? Great, excellent.
I can just mention one thing regarding USB. You want to have the position signal sent over USB instead of using these sine and cosine signals, right? That was the idea. Yeah, but the problem is that it's much harder to work with USB in a timely fashion than it's to work with this audio signal, because the way that the audio interface operates is that it has a minimal buffer, and then it just sends that over a USB to the host computer. And the host computer API for handling audio class data has been optimized for performance. So that part, believe it or not, both in Linux and Windows works, which means that you will get presented with extremely low latency. You can have buffers down to 32 samples, which means that you have 1 millisecond approximately of delay.
I guess they use either product.
Yeah, well, I don't know what magic lies behind, but it works. So low latency is perfectly possible using audio class devices. Yes. It's a bit harder to do with to rely on the kernel and drivers and everything to get timely data in other USB formats. So,
I'm thinking the same.
Yeah.
So we continue the discussion later.
Yes. Okay.